All right, so we're going to take a look at phase change or heating curves and also how we tie in specific heat and energy change. But now we're going to look at an energy change when we're changing states of matter as opposed to we were changing temperatures. So when energy is added or removed from an object, two things can occur. All right. One, if there's no phase change occurring, so it's always a solid or always a liquid or always a gas, then you can change the temperature. And that's going to change the kinetic energy. It's going to make the molecules move faster or move slower. The other thing that can happen is we can use the energy to use it to change phases. So when we're going from a solid to a liquid or from a liquid to a gas or vice versa, then that energy is being used to either break or form intermolecular forces between the molecules and no temperature change occurs. You cannot change temperature and phase at the same time. You only change one or the other. And we can use this to create something called a heating curve, all right, or a cooling curve. And it just shows the different states of matter. And it kind of shows as energy is added over the x-axis, how does temperature change occur? And then we can kind of explain what's going on. So, all right, if we look at A, all right, at point A, we have a change in temperature, right? Temperature, starts at the bottom and then it ends here. So our temperature went up, all right, which means we're going to be a state of matter, and the state of matter that exists in general at the lowest temperatures is a solid, all right? If we jump ahead to C, we start at a temperature here and we end at a temperature here. So this is also a single state of matter. If this is a solid, the next state of matter up would be a liquid. And then E, same idea. We start with a temperature here and we have a temperature up here. Our temperature is changing, which means we're a single state of matter. So E would be a gas. All right. All right. Let's look at B and D. In B and D, the temperature does not change, stays the same. All right. B and D, no delta T, no temperature change. All right. So these are phase changes. Because we're heating this, B is evaporation, and D, oh my goodness, no, it's not evaporation. So sorry. D is melting. I am so sorry. D is evaporation. Vaporization would also be okay. All right. So if we look at this curve real quick again, let's label them. All right. A is a solid, and C is a liquid, and E is a gas. So in order to go from a solid to a liquid, right? So to go from a solid to a liquid, all right, we break some intermolecular forces, right? Originally, everything's locked together in like this rigid pattern, but we're able to break enough of these intermolecular forces that these particles they can move, they can flow past each other. That's why a liquid can change shape. It can take the shape of the container because the particles can move. So we have to break some intermolecular forces when we go from a solid to a liquid. When we go from a liquid to a gas, all right, one of the ideas behind a gas is that when you're a gas, there are no intermolecular forces present. In fact, that's one of the things about the ideal gas law is that they don't have intermolecular forces. All right. That means you have to break all IMFs. All right. Instead of just some. All right. All greater than some. So it always takes more time and more energy to go from a liquid to a gas compared to a solid to a liquid. And the opposite is true. It's going to take, all right, more time for the gas to fully condense into a liquid versus the liquid fully freezing into a solid. All right. We have this concept of heat of fusion, the heat of vaporization. And this is the energy required to change states of matter. And it's recalculated based on how much energy is required to break intermolecular forces when we're going from a solid to a liquid or a liquid to a gas, or how much energy is released when we form intermolecular forces, like going from a gas back to a liquid or a liquid back down to a solid. Right? So we use these two formulas. Now, here's the bummer, right? The formulas are not given. Okay. However, okay. However, H fusion and H vaporization, their units usually help you figure out how to solve for the amount of energy. So if H fusion's units are kilojoules per mole, if you multiplied it by the number of moles, you'd be left with kilojoules. All right. And that's the same idea as that formula right there. That's why they don't really give you the formula. All right. But that's the idea. So let's take all this stuff we've learned so far and put it together in this question. All right. So I recommend pausing for a second, trying this out. All right. And then I'll take you through both parts. Okay. So it says calculate the amount of heat needed to purify a mold of aluminum at 298K by melting it. They give us the melting point and then the molar heat capacity and the heat effusion of aluminum. So we want to know how much energy we have to melt the aluminum. So we have aluminum, that's a solid. We have to get it to the melting point, and then we have to melt it. Okay. So we have to figure out how much energy is required to do all of that. Well, if we're looking at this problem and they're giving us molar heat capacity, all right, heat capacity, think about C, specific heat, all right, we're going to use the equation Q equals MC delta T to start. Now, when we use this, all right, this involves a temperature change. So this first step is to raise the temp to the melting point. All right, so Q equals, all right, we have M is molar mass. Well, we have 1 mole. And if we look at our molar heat capacity, it's also in moles. So we can keep everything in moles. So Q equals 1 times C for this is 24. And then times our change in temperature. Well, our final temp was 933. And our initial temperature was 298. So if we solve, right? Type in and solve for all of that. We get 15,240 joules. So that got us to the melting point, but we didn't melt it yet. Now we have to melt it. I'm going to do that down here in a different color. I'm going to do that in red. All right. So to melt it, I can't use this equation because if I try to use this equation when I'm melting it, delta T would be 0, and then this would just go away. So we can't use this equation, but we don't. They are telling us, all right, they are giving us some information right away. They're telling us, hey, the heat of fusion, all right, good old HF is 10.7 kilojoules per mole. Well, it turns out if we take our 10.7 kilojoules per mole and we multiply it by 1 mole of aluminum, the moles cancel out and we're left with 10.7 kilojoules. So this was to melt it. So it took 10.7 kilojoules to melt it. And in step one, it took 15,240 joules to raise its temperature. Well, we need to find out the total value here. So we're going to add these two numbers together, but we can't add them together like this because the units aren't the same. So I'm going to convert this number up top from joules to kilojoules, and it's going to become 15.2 kilojoules. Okay. Move the decimal 3 places to the left. So now I'm going to add up my two numbers. So 15.2 plus 10.7, and we get 25.9 kilojoules. So this is how much energy it costs, all right, to raise and melt 1 mole of aluminum. Okay. Now we want to compare it to the bottom. The bottom says to get aluminum from aluminum oxide, they give us this equation. So solid aluminum oxide produces 2 moles of aluminum and 3/2 moles of O2. And they give us the delta H value as 1,675 kilojoules per mole of reaction. So, all right, up top is 25.9 kilojoules. If we want to find out, okay, how much energy does it take to get this out? Well, here, let's use what we've got. Okay. All right. 1,675 kilojoules per mole reaction. Okay. For every one reaction, there are 2 moles of aluminum. Right. So we want to find out how. Okay. So if we look at this, all right, reaction cancels out. And now we're going to find out, hey, how many kilojoules per 2 moles? So 1675 divided by 2. All right. And that's going to get you 837.5 kilojoules per mole of aluminum. Well, up top, it was 25.9 kilojoules per 1 mole. And at the bottom, it's 837.5 kilojoules per mole. So the question is, which requires less energy, recycling it or extracting it? The answer is recycling, because that's the answer for recycling, while extracting, boo, took this much.